kind of an important recording today, I guess. Let's see here. Our last chapter, chapter 21. This is our oh, sorry. Thanks.
Hi, good morning.
Thank you for coming. It's our last chapter. So last day of new material, and then you'll have the overview and everything can settle down. That's what I love about studying for a final exam is there's nothing more coming at you. This now you can kind of have the overview, and I always find that that makes it, you know, a little bit easier. So our final exam, I was gonna ask, but it's hard to get a handle on it. Has anyone tried to find a data set? No? I'm worried it's too hard of a task.
Well, for a group of 5, this could be fun.
Well, that's what I was hoping, but I do have a data set that I've made up, so it randomly generates, which means it's not very good, but at least you can answer questions about it. So I'm wondering if we want to do that instead. I'm happy to let you use your own data set, but it feels like you guys are kind of busy. So so maybe it would be better if I gave you a data set. So question hand or comment hand?
I'm doing a similar project in Susan's class. Am I allowed to use that same data set, or do you recommend using a different one?
You can use the same one. I don't see why not. But maybe it's easier if I just give you the data set.
Yeah, it will be good for backup.
Yeah, right?
Yeah.
Okay, well, let's pivot on the mini project then, because yeah, I was thinking about it yesterday, and I fear it might be too big of a task.
This is the right room. Mine's the right room.
I don't know. I don't remember why I wrote final exam.
I don't know. That's a good question.
Yeah, I guess I could April 17th from 6 to 9. I feel like I've already written this in S104, that huge auditorium. So that'll be us. Yeah, I don't actually remember why I wrote final exam, but let's do a smidge of review. Right, we wanted to, so last day we compared 2 independent sample means, right? So we had 2 samples. So we had 2 samples of numerical data. For numerical data, we analyze the means, right? And so here we analyze the means or the mean. And what did we say? Well, if I want to compare these 2 samples, so if you think about in Excel or in your spreadsheet, right, you would have variable 1, which is a numerical variable, and you'd have variable 2, which is also a numerical variable. Okay? And you'd have some number, right, because it has to be a number for numerical data. at the end of all these, we would have an average or a mean, right? And we would find X bar 1 and X bar 2. Those are your two sample means. Okay? But really what we're interested in is our hypothesis that mu1 minus mu2 is equal to 0, meaning there's no difference between those two, right? If the difference is 0. And so our best guess at what mu1 minus mu2 looks like is x1 bar minus x2 bar, right? And then we needed the standard error, right? And so it involves the standard deviation of both these groups, right? We can calculate S1, S2, and our sample sizes N1 and N2. So our test statistic has to involve all this information, right? It takes our point estimate, right? We know we end up with a T because this is review, but our point estimate is X1 bar minus X2 bar. Right, that's our best guess at what this thing looks like. I'll scroll up just a smidge, right? Our point estimate for mu1 minus mu2. Technically, what color can I use? I'll use light blue here. Minus mu1 minus mu2. However, when we assume, and we have to assume that the null hypothesis is true, right? This is going to be 0, so we subtract 0. But just as a reminder, we're going to see how far is the difference in the means that we saw in our sample from our hypothesized difference of 0, right? That's technically what we're doing. But on our formula sheet, I'm just going to have x1 bar minus x2 bar so it doesn't get too boggy. And then we had our standard error. Our standard error of x1 bar minus x2 bar is s1 squared over n1 plus s2 squared over n2. And if you play around with this thing, this formula, okay, it doesn't matter which group you assign to be group 1 and group 2, right? The only thing that would change is the sign in your numerator. Right? Your denominator would just switch, but a plus b is the same as b plus a, and so it doesn't matter. Okay? Once you have your t, you can calculate the p-value, right? Using the t dot dist or a t dot dist right tail or two tail, depending on what? Depending on your alternative hypothesis. Right? Mu1 minus mu2, let's say, is not equal to 0. If you wanted to show a one-sided or do a one-sided test, you'd have to think about how you calculate the differences, right? And think about how that would relate to 0. Okay? But like I said, this is all review, and so not what we're going to do today, but let's see here. And then we also built a confidence interval, right? But once you have a t, you know how to find the p-values for t, right? And so using the t dot dist or some version of it, if you want to get fancy, you can always work with t dot dist, right? But if you want the right tail, right, the upper tail, you can use the t dot dist right tail. Okay, now today, I know, so abrupt, because what was the confidence interval? Our confidence interval is just going to be our point estimate plus minus our t star, which is going to determine the width of my interval or my confidence level, times the standard error, which is going to be the same, right? Oh, and I guess we should, the degrees of freedom is going to be, we're going to use the minimum of n1 minus 1 or n2 minus 1, smaller sample size minus 1. Thank you. Applause is always nice. All right, so today we're still going to analyze two samples of numerical data. Which is still going to look like this in our Excel. All right, if I snag this. Make it little there. So we're still going to have variable 1 and variable 2, and we'll have some numerical variable or numerical data in each of these variables. We are still able to calculate the mean and the standard deviation, and they each have a sample size. But what's going to be different is that these samples will be paired now. Okay, and so there will be some natural pairing. Okay, and so paired data. It's a special case of two numerical variables. Okay, and so we have, oh, and I need this little bit of space here. We have paired data. Sometimes if I call it matched pairs, sometimes I call it matched pairs just to emphasize that it's paired. But we have paired data if we have made two observations on the same subject. If we have made, and I'll say made two observations, hold your applause. On the same subject. Which means that our Excel is going to change a little bit, right? We've got subject 1, 2, 3, blah, blah, blah. And now I've made two observations on the same subject. Okay? Not necessarily the exact same subject, but if you want to kind of capture variability, this is one way to do it. So for example, if you're making a measurement, I've got one example where we have windmills, I think it is, kind of power generators in different locations, but we would consider them paired on the day, right? And so because if there's a super windy day, right, we would expect more power to be generated than on a day that's not windy, right? And so then we would pair those observations on the day, right? So it's not necessarily on the same subject, but if you want to eliminate some variability, right, and you're able to create pairs, right? I'm thinking water measurements, right? If it's a super stormy day, right, then the water's all whipped up and maybe your measurements would be different than on a calm day, right? And then you'd want to capture that.
Like if you're measuring, say, discharge.
Yeah.
For that year, you're like two different.
I would say those would still be two independent samples. Yeah. Unless there's a way to say that this observation so I'll use my pointer here. This observation here is paired with this observation here. If there's no natural pairing, then I would just say that they're independent samples. Okay? And that's this analysis here that we did. And so we can already do that. But now we've got the special case, right, where we have natural pairing between the two. And so here, let's say, here we have a natural pair. Some common examples include kind of pre-post scores or measurements. Right? Before and after studies, right? Because as long as you go back and you measure at the same location after something has been done, right, then those would be considered paired, right? And that's what the example that I have here. But what's the trick that we're it's about to get kind of boring. No, not boring. But one cool thing that we do is because we have these natural pairs, right? What we do is we calculate the difference, right? The difference in the pairs, right? Because that would indicate a change on that day, for example, right? It would indicate a change at that location, right? In that individual writing a pre-post test, right? And so we're capturing that that day or that location. Okay? And so what we do is we calculate the difference. Now we're going to have a sample of differences. Okay? And so here you'd have a number, a number, a number. And now I have everything that I need captured in those differences, which means I can essentially kind of toss this out, right? Or you just kind of ignore it now. Okay? And what we do is now we have one sample of differences. Okay? And so now we're able to calculate the average of the differences. I can calculate the standard deviation of the differences. Right? And I have a sample size of the differences. I like to put a little diff, a little subscript diff on there. Sometimes we just use a little subscript D. I've even seen D bar, but I find that kind of confusing. And so I use X bar of the differences, right, with a subscript diff. We can calculate the standard deviation of these differences, right? Imagine your spreadsheet, you've got your differences, you know how to find the average, how to find the standard deviation, and you've got your sample size and diff. Need another page here. So to analyze paired data, it is possible to have paired data for categorical variables, but the analysis is beyond the scope of this course. So there. So for us, paired data is only going to be numerical. So to analyze paired data, we calculate the differences, the difference for each observation, or a subject, I should say, for each subject. And then we analyze the mean of the differences. And then we analyze the mean of the differences. So our null hypothesis is going to look like this. Mu diff, right? The overall population difference, right? Mean of the differences as opposed to the difference in the means from the two sample situation. And so words get kind of tricky. It's the mean of the differences. And what we want to know is, okay, well, if there has been no change from pre-post, I don't know, post, I think there's a water filtration system or something that was implemented, right? And so if there's been no change, the difference between these two things would be 0, right? If the measurements stay the same and no change has happened, then the mean of the differences would also be 0, right? And so what we do for paired data is we always have our null hypothesis is always that mu diff is equal to 0. That's really nice because once you've decided that you have paired data, this will always be your null hypothesis. For paired data, this will always be our H naught, the whole thing. So it's figuring out if you have paired data, right? That's the pickle. And then once you know that, then you have your null hypothesis. Your alternative hypothesis is going to depend on how you calculated your differences, right? Especially if you want a one-sided test, not if you want a two-sided test, then it's just not equal to 0, right? If you care about both directions, right? But how you calculated your difference, right? Variable 1 minus variable 2, if there is a change, right? If variable 2 is lower, let's say, than variable 1, then so let's call this 1 and 2, or that doesn't make sense, A and B, right? If I want to show that there's a decrease after something's happened, right? Then I have a high number and a low number. High number minus a low number makes still a positive number, right? So greater than 0. Another way that you could do it is you could check, because I have to give you the mean of the differences and the standard deviation of the differences. Okay? And so, or you'll have them. So you can always look at the mean of the differences. And if it's positive, then your alternative, if you want a one-sided test, should be that it's greater than 0. And if it's negative, it should be that it's less than 0. Right? And I picked an example, or I generated an example that is one-sided, so we can have a look at it. Okay? But in your alternative hypothesis, still has to be about how mu diff relates to 0. Okay? But this sign, or the inequality, let's say, depends on how you calculated the differences. Okay. And like I said, we have an example coming up. So for those reasons, I like to make it a two-sided test, right? But then how does this read? The mean difference is significantly different from 0. Ugh. Right, so you want to take it nice and slow, right? Is different from 0. Okay, so a little bit tricky, but it is a one sample mean type of question, right? And so now I just have one sample of differences. It's just a special case of one sample means, which means we already know how to calculate your test statistic. T is going to be, remember, from before it was x bar minus mu naught divided by s divided by root n. That's a one sample mean type of test statistic. Okay. Now, all I'm gonna do is slap some diffs on there. And we still assume that the null hypothesis is true. So the mu diff, my null hypothesis says that mu diff is equal to 0. Right? And so this is always going to be 0. H naught says that mu diff is equal to 0. So usually all I give you, just to simplify things, is x bar of the differences divided by s of the differences divided by the square root of the number of the differences. So it's just got little diffs on there, or d's if you don't want to, but you do have to indicate that it's the differences somehow, right? And so diff or d's, I find diff makes it very obvious what it is. Okay. What about our degrees of freedom? If it's a one sample means type of question, our degrees of freedom for our t-distribution is going to be n diff minus 1. Right? The number of differences minus 1. The only thing I find can be confusing to a lot of people is the n diff, right? The number of the sample size of the differences. Right, but if you read it like that, the sample size of the differences, then it has to be this number, right? This sample size, which the only reason it's confusing is because it came from 2 samples. And so you might be tempted to think about, oh, well, I had this many observations, right? But we're now focusing on the number of the differences, right? So that's my caution. But then I have a t, right, which is going to be measuring how far is the mean of my differences from 0. Right? I'm going to be able to find how many standard errors my x bar of the differences from my sample is from 0, right, at n diff minus 1 degrees of freedom. And then I have my p-value. Once I have my p-value, then my conclusion stays the same, right? If the p-value is less than your alpha level, you have enough evidence to reject H naught. And then whatever that means in terms of the question. The conditions, we'll just briefly touch on them. Paired data, right? We analyze the differences. So we check the conditions for the differences. And I'll emphasize one sample of differences. They have to be the same because they have to be paired. Good. Let's see here. So here, this was the question. N1 has to be the same as N2. Otherwise, you don't have pairs. Nice. So our conditions, we have to check for independence. Now, our independence gets a little bit weird. but the differences have to be independent of each other, right? Meaning that the subjects or the things that we've paired things on have to be independent of each other. Okay? And so differences must be independent of each other. So that is locations or subjects, etc., must be randomly selected. If they are, then we can assume independence in the differences. Now, sometimes we throw in the fact that the data has to be paired, but at this point, I'm assuming that you've already determined that it's a paired data scenario. And so I'm not going to use that as part of the conditions because you already decided that that's the type that you have or the type of question that you have. But the normality condition is the same as for a one sample means type question. If the sample size is bigger than 30, you can just go ahead and assume normality, right? That's the beautiful thing about the central limit theorem. Okay. So if n is greater than or equal to 30, we may assume normality.
Here is the number of pairs.
Yeah, thank you. I'll sneak that on there. So if you have a large enough sample size, right, and that's one of the reasons why it's so ingrained in us, right? Oh, well, you should have a big sample size, right? Even heading into this course, you probably had a good understanding of, well, you got to have a big enough sample size, right? And the reason for that is because you have to be able to assume normality. Okay? We don't know that, right? But we do understand that, okay, I need a bigger sample size, right? Because what happens if you increase your sample size, things become more stable, right? You have more reliable estimates. Okay? Whereas if n is less than 30 and diff is less than 30, then we have to do a little bit more poking around. You can make a histogram, right, to make sure that it looks approximately normal. Okay? Or you just have to assume that you're drawing from a normal distribution, okay, which is kind of harder to wrap your head around. So if the sample size is less than 30, we can make a histogram to ensure the distribution looks approximately normal. Now, depending on how desperate you are to continue with your analyses, you can be kind of flexible here, right? And so that's probably bad advice, but it's true. I've worked on enough research projects to know that, oh, yeah, but, and then you develop some argument like, if I had the resources, which means give me more money, to collect a larger sample size, I'm confident that it would approach a normal distribution. Right? So, okay.
Can you make QQ plots in Excel?
Hmm.
Or is that kind of an or?
I don't know. I haven't tried. I'm curious though if you can make QQ plots. So a QQ plot is used to check normality, and you're basically looking for a diagonal line, Now, yeah, I'm curious. It's not something that I expect us to do, but and so, but I am curious. I don't know. But the thing about Excel is they only just recently made it so that you could make a histogram just kind of out of the bag. So they're kind of behind on the statistical analysis. And with R and Python and all those, it's like there's not really a point for them to focus on it. So I suspect no, but I'm curious to have a look. Just so, or a QQ plot. But we won't see them. So you can ignore that. But just because we talked about it, you can use a QQ plot. Okay. There's also, and I can't remember what it's called, but there's a hypothesis test to check for normality. You can do a hypothesis test for your conditions for your hypothesis test. Yikes. I know. But that's the beauty of all the things that we're doing here. What do you need just to be able to do a hypothesis test? Even if there's a hypothesis test that you haven't necessarily seen before, what do you need? You need to know the null hypothesis, right? That's important. And you need to know what the test statistic is, right? And then if it's a new distribution, there are other distributions than what we've seen. But if it's a new distribution, you need to know how to find the p-value, right? But once you have a p-value, then you know what to do, right? You have your conclusion. The conclusion's always the same, right? If your p-value is small enough, less than the alpha level, you have enough evidence to reject H0. And then from earlier, you know what your null hypothesis was. So there's tons and tons and tons of hypothesis testing that you can do, but we developed the core toolkit here. And then I let you fly on your own, or you can fly on your own. For a confidence interval, we have our point estimate. Our best guess at mu diff is X bar of the differences. And maybe what I'll do is I'll just do let's do the one sample mean version first. And then I'll do the exact same thing where I just throw some diffs on there. And that T star is going to come from a T distribution, right? With N diff minus 1 degrees of freedom. So for us, we're gonna have X bar diff plus minus T star times S diff divided by the square root of N diff. Same standard error as the test statistic, which is really nice for means. Proportions make us work for it, right? They're different depending on if it's a confidence interval or a hypothesis test, right? But here, right, for means, we settle down and it's just one standard error, which is really nice. Okay. We ready for an example? A resounding yes. No, not quite. So I got ChatGPT to make an example, but I guess I could have gotten there by myself, but I was too tired last night. And before I read this, let me just see if I can load this Excel See, I made an Excel sheet last night, but now how do I find it? That's the question. Chi-squared. No. Wonder what I called it. It's not updating, I think. Or did I put it in here? No. Come on. And of course, I looked at my laptop and I said, nah, I don't need that. Okay, well, I have an Excel spreadsheet that is not available to me. That's okay. We'll just make it up. So here's the scenario. A local environmental agency is monitoring the quality of water in a river before and after. So that's our clue, right? That it's going to be paired data. It's just someone out there, but they don't want it here. Just hanging out. Before and after an industrial facility installs a new filtration system, the agency collects water samples from the same 20 locations along the river before and after the filtration system is implemented. Okay. So the primary concern and the thing that they're measuring is the level of the dissolved oxygen in the water. Okay. As low dissolved oxygen levels indicate poor water quality. No. Is there evidence of a significant increase in the mean dissolved oxygen levels after the filtration system is installed? Which would mean what? It would mean that the filtration system is improving the water quality, right? It's kind of what this is asking, right? And so here, of a significant increase in the mean dissolved oxygen levels after the system has been installed.
Data set?
I did, but I can't seem to get it. I don't know why. Is my internet plugged in? Must be, because I'm on Zoom. Yeah, I don't know why it's gone missing. Did I have the wherewithal to put it on Moodle? I don't think so.
Need a different water question. I have one right here.
Oh, nice. That's okay. We can just make up some values.
Sounds good.
Oh, I am glad I hopped on here, actually. I slipped up, and I'll do one assignment for Tuesday and Thursday. But it makes it a nice 20 even assignments. And then that'll be your last assignment. And then, well, as you can see, hidden from students, but there's another bonus assignment coming up. So how I've set the assignment with the bonus assignments, if you do them, you can replace a lower grade, but if you don't do them, they'll just get dropped, right? So your assignments are set to drop your lowest two assignments. And so if you do these, if you miss some, then you can do these and bump them up. So this one, you're doing me a favor, so I make you work hard for it. For the first one, for the statistical process control, it's a video assignment that I've made, and you guys are my guinea pigs. Because no one has done a run through. Well, I've done enough run throughs to feel comfortable putting it out to a class. But before I put it out to my first years, I want to see if there's any issues. So if you're if you're okay to step through it and have a look at it, and let me know if there's any issues, right, or anything confusing, then please let me know. But this one, I made it due on Sunday. Yeah. Yes. So, but it's pretty fun. So, let me show it off. So here, so what you do is, so I've got a little introduction there because we're just going to use kind of rough approximations for these, for the bounds. But if you want to be more proper, you can read the chapter there. But if you hit the play video.
This video is about control charts. First, we discuss what control charts are and why you need them. Then we are going.
So then it runs through and it introduces the concept, and then it'll pause and bring up a question and you answer the question. And then once you've answered the question, you can play another snippet of the video where she introduces a concept, and then there's another question. I think there's like 3 or 4 questions, and you pick your way through the, yeah, so it's my first video assignment that I've made. So I know Steve's always showing me up. He made one before, but I think mine's better. So you can try it. It's just an 11-minute video. So how long can it be, right? Okay. Let's see here. I kind of got sidetracked, didn't I? Nope. Oh, I should post this for you guys. It's an inference decision tree. If the P is low, then the null hypothesis must go. You can decide what type of question you have, right? Do you have a proportion question? You could have 1 sample, you could have 2 samples, you could have 3+ categories. Now, we didn't do a chi-squared goodness of fit test, but we did do a test of independence. And I'll post for the means. You can have 1 sample, you can have 2 samples, which will split into paired data, 2 independent samples. Or you can have 3 or more groups, which is an ANOVA, which we're not going to cover in this class, but I will post a bonus assignment on it, just in case you wanna brush up on an ANOVA. Okay? But you do have to. It just replaces your lowest grade. I know, Steve and I talk about that a lot. He's like, there's got to be a way to shift, like he wants, and I would want that too, but he's very concerned about it. He wants it to make it so that you can have more than 100% on your assignments, but Moodle doesn't let us do that. I know. So
I literally have one.
you can, you can on individual assignments, but there's no easy way to have it, or at least that Steve and I can figure out, so that your assignment grade can be over 100%, unless you have, do you have something like that? Individual assignments, yeah, I can do it over 100%.
Yeah, I mean, I guess it's like a midterm grade, that the bonus question.
Yeah, the bonus question. We'll see how many are affected. Something tells me not very many. Okay, anyways, so now you've seen those bonus assignments. But it looks like I did not post my spreadsheet. And I'll try again, because why not? Maybe it's on the cloud. Chi-squared, no. Can I search? Paul, no. don't know where it went, and that's pretty annoying. So let's imagine we have our Excel spreadsheet, right? What's it gonna look like? That's a good place to start, right? What if you had this scenario and you collected data, right? What would your spreadsheet look like? And that's gonna be a good clue. So your spreadsheet might look something like this. You've got your location, location 1, 2, 3, all the way down to 20. You're going to have a measurement before. Now, I gather that dissolved oxygen levels tend to hover around 5, and so obviously it'd be easier if I was able to use a random number generator. But let's see, because humans are notoriously bad at making random numbers. So at location 1, before, we had a dissolved oxygen level in milligrams per liter, 4.98, and then I had 5.01, and then I had let's say 3.7. That's bad, is what I've gathered. Right. And let's do up down to 6.4. You know what, for simplicity, how about we just use 1 decimal place? I'll change this to 5.1. Just because I'm gonna have to do the differences. Ugh. Hopefully you would measure with more precision than 1 decimal place. But I already know I have to calculate the differences, and so I don't want to do that. Then they install the filtration system. And we presumably let some time pass, and we go back to the same locations, and we measure the dissolved oxygen level after. Now, let's think about the reason we want to pair these things is because at location 3, we had a very low dissolved oxygen level to start with. So even an improvement might be low compared to the rest of the measurements, right? But to see an improvement, we would have to go from 3.7 as opposed to, let's say, 6.4, which is on the opposite end, right? Very, very high. An improvement would have to be even higher than this, right? And so if we're looking for an improvement, right, it's within each location, right? Very similar to, I usually do an example of a running group, right? And so if you start out as a fast runner and you join a group and you see improvement, then you started out fast, you're gonna be really, really fast, right? If you're a slow runner and you improve, you're probably still, even improving, you're still a slow runner, right? But there's been improvement. And so to capture that, right, variability between runners or locations, right, then we analyze the pairs, right? Because then we're able to see an improvement. Whereas if we just analyze the before minus the mean of the afters, all that would get muddled, right? You would put those into 2 big groups and compare them, and you would lose that that blocking mechanism. I'm stalling. 5.2, because I hate making up numbers. 5.0, what? I know. Can happen. Why was this a what? It's actually decreased, which is not an improvement, right? It's the opposite. I don't know. Deprovement? No. 3.7 inched up to, let's say, 4.8. That's great. 6.4, maybe there's an upper level. I don't know. So now, because we've determined that we want to treat these locations as pairs, right? This is paired data because we want to capture that kind of between location variability. And so then we analyze or we calculate the difference. I tend to do it in the order that they appear. And so how I'm going to calculate the difference is before minus after. But if you did after minus before, right, that's going to change the sign of those differences, right? So if I'm talking about before minus after, and I want to know if there's been a significant increase, I'm expecting generally negative values here, right? Because I want a higher in the after value. Okay? So generally negative. Whereas if you had after minus before and you want to show that after is higher, you'd have generally positive numbers, right? The amount of the difference, right? The magnitude of the difference is going to be the same. Okay? It's just the sign of the difference that's going to change. So 4.9, where's my trusty calculator? And this is why I made an Excel sheet, so I wouldn't have to do this. 4.9 minus 5.2 is negative 0.3. 5.1 minus 5, okay, that one I can do. 3.7, no thanks, minus 4.8, I get negative 1.1. And 6.4 minus 6.5, negative 0.1. I know. I don't care. I have a math degree. I'm done doing math. Okay, so now we have these differences, which means that now we're going to focus on these differences, right? Which also means that effectively you can, I'll remove that, but you can ignore that. You've captured all that information in the differences. Right? I'm going to remove that because it's kind of misleading. Okay? But right, once you have the differences, then that's your focus. Okay? Now, we can calculate the average for each of these. Right? I'll make something up. So here we can have the average. Oops. We can have the standard deviation, right? We can use Excel to calculate all these. The average before and the standard deviation of the befores, the average after and the standard deviation of the after measurements, right? But then we'll also have the average of the differences. And so here, let's say X bar before, let's say was, let's make something up, 4.9. The standard deviation of the befores, let's make it 2. Actually, sorry, let's do 1.2. we can calculate, oops, after, X bar after. Let's say it's 5.3. That's an improvement. And the standard deviation of after, let's say, is 2.1. X bar of the differences will be the difference in the means, but the caution is that the standard deviation doesn't behave the same way. Okay? And so just to make it match, let's see, 4.9 minus 5.3. I get a difference of negative 0.4. That's an improvement, a general improvement of 0.4 in your dissolved oxygen level. Nice. And then the S of the differences, I just have to make sure I don't pick 1.2 minus 2.1, which is negative 0.9. Let's do is 1.3. So here, notice S diff is not the same as S before minus S after. And that's because of, if you think about how the standard deviation is calculated, right? We're doing squares and square roots and all that fun stuff. And so it's not going to be linear anymore. And so that's why you want to be really careful. Whereas the averages, right? You add things up and then you divide by n and that'll still work. Yeah, but that's one thing to notice. But once we have, and I guess I should jot down our sample size. We have n before, n after. Now for it to be paired, like we said, these two things should be equal to each other. Otherwise you don't have pairs anymore. And then we have n diff is equal to 20 in this case, right? The number of differences. I'll do equals 20, and they should all be equal to each other. So now I have all my sample information and I'll highlight it again here. This is the chunk that I'm going to be working with. That's the information that I'm going to analyze. Okay, so we wanted to know, and the only thing that I I calculated proper differences and proper values here. I've just made them up in the Excel spreadsheet. And another thing that I did, because we only have 20, is I also had made a histogram of the differences, but it looks approximately normal. And so we're good to go. These I don't know because I only did 4. Let's check our conditions and get those out of the way. First, independence. Independence of the locations in this case, right? Can we assume that the locations are independent of each other? And so I don't think it says that the locations were randomly selected. And so what do we say? We say we assume the locations were randomly selected, right? Or if you want to cut to the chase, you can say we assume the locations are independent of each other, right? Those two would mean the same thing. So we assume the locations were randomly selected. And therefore independent of each other. maybe I'll put this on the next page so it's together. The normality we have a sample size of 20 and diff is equal to 20, which is less than 30. So then we argue that the differences follow approximately a normal distribution. So we must assume, since I've somehow lost my spreadsheet, the distribution of the differences is approximately normal or, again, you can kind of cut to the chase because really what are we after? Or we have to assume that the distribution of dissolved oxygen levels in the stream is approximately normal. Or we must assume the distribution of dissolved oxygen levels in the stream are the distribution of dissolved in the stream is approximately approximately normal, right? If we're drawing from a normal distribution, then there's no reason to think our sample would be anything but normal, right? And that's really what we're talking about there. Conditions, who cares? So, is there evidence? Well, that means I have to do a full hypothesis test. Is there evidence of a significant increase in the mean dissolved oxygen levels after the filtration system is installed? Now I'm going to sneak it in here. My difference was before minus after. And we want to know if there's been an increase in the after scores. Right? How does that relate to 0, right? And this is where I say, okay, this can be kind of tricky, right? If you think about before and then you increase your after from before, then you're going to have, you can pick numbers 2 minus 3, for example, you get a negative value, right? And so then if there's been an increase, then the difference is less than 0. Okay. So if there has been an increase, the difference, because of how we calculated it, right? If I did after minus before, I would get positive differences, right? And so that it depends on how you calculated the difference. But if there's been an increase in the difference, the mean difference would be less than 0. Another clue is that if you want a one-sided test, you can only use a negative value to show that it's less than 0, right? And you can only use a positive value to show that it's more than 0, right? Unless you've kind of fumbled your hypothesis, right? That can happen. But for a one-sided test, the only thing I would want to use negative 0.4 for is to prove that it's significantly less than 0, right? I can't use it to prove that it's more than 0. Right? So you can always use your data as a clue. So now, for our hypothesis test, step 1 is to state your hypotheses. we've decided that we have paired data, which means that we know that the null hypothesis is that mu diff is equal to 0. Right? It's just the alternative hypothesis making us work for it a little bit. How does mu diff relate to 0? Right, from what we were just talking about here, right? It should be less than 0 if there's been an improvement. Because I'm only concerned with if there's been a significant increase after the water filtration system. It doesn't seem like we care if there's been a decrease, although that would be a concern as well, right? And so then that's why we should be doing two-sided tests always, right? Not equal to, but just to see how the differences work. It's better to do a one-sided test here, but in general, right, we should just do a two-sided test because we would be just as concerned if the dissolved oxygen levels actually decreased, right, after the water filtration systems. In fact, I think that would be more concerning. Right? So this here is what makes it a one-sided test. Which means I need a one-sided p-value later on. Step 2. Do the test. Do the do. Calculate the test statistic. T is x bar diff, technically minus 0. If you like the minus 0, you can put it on there, but I'll just have the x bar diff over s diff divided by the root of n diff. I have this information. So what did I say it was? Negative 0.4 and 1.3. Negative 0.4 divided by 1.3 over the square root of 20. I have no idea what is in store, so let's see. Right, and just technically, how far is negative 0.4 from 0? From a difference of 0 is really what we're after. But let's do 1.3 divided by the root of 20. Okay, so far so good. Negative 0.4 divided by that, I get a t of negative 1.3760411832. In terms of our t distribution, right, just to throw that in here, our t distribution, we know what it looks like, is centered on 0. Okay. And so what we found was that our difference is negative 1.376 standard errors below the mean. That's not very far, right? As a kind of a general threshold, right, we have to be roughly 2 standard deviation or standard errors away to be considered significantly different, right, roughly. So I suspect I'm not going to be able to reject H naught, right? But we need a p-value just to formalize that, because the p-values, although confusing, right, when we first start, it's easier to communicate in probabilities, right, than the t, which you would have to communicate, okay, well, because I was 1.376 standard errors below the mean or the hypothesized mean difference of 0, right? That gets boggy really quick, especially if you're talking to your boss. So they want to know, okay, the probability of seeing this if the difference is 0 is what? And that's the p-value. So step 3, find the p-value. we need our degrees of freedom is n diff minus 1, which is 20 minus 1, which means I have 19 degrees of freedom. In Excel, I need this area here. This is my one-sided p-value. It's a one-sided test, right? And so I'm only concerned with the lower tail, right? And so that's why this is the area that I want. Okay. So in Excel, we will do equals t dot dist. That's going to give us the area to the left. And then there are the other options, right tail, two tail, depending on what you want. But we just want the left tail, and so that's good. Negative 1.376 with 19 degrees of freedom. And I think it needs to know that we want cumulative to be true. I'll hop into I guess a random Excel spreadsheet and see what we get. Equals t dot dist of, let's see, where's my negative? Negative 1.376, I think it was. And then it prompts me for my degrees of freedom, which we have 19. And cumulative is true. No brackets. There. I'll screenshot this. This is a little bit bigger. All right, I get the area in the lower tail is 0.092413. And if you had a two-sided test, you'd have to multiply this by 2 to replicate it in the upper tail, which makes it harder to reject H naught. Right, and so that's why we should be doing two-sided tests. But for this, just for practice with the differences and all, we're doing a one-sided test. Okay. Step 4, your conclusion. That's the moneymaker. It's always the same, which is nice. Our p-value is 0.0924, right, 13. Let's assume our alpha level is 0.05, just as always, right? Then I do not have enough evidence to reject H naught, right? It could be tempting to look at this and say, well, if I use an alpha level of 0.1, then I could reject H naught. That's called fishing, and you don't want to do that, right? And so it's always important to pick your alpha level beforehand, before you do any testing, because otherwise it's so tempting to say, well, if I really want to reject H naught, right, then I'll use a 0.1, right? But that's something that you should have kind of determined before you went ahead and did all your data collection even, right? So we're going to stick to 0.05, which is kind of a womp. Why? Because it means that we don't have enough evidence to reject H naught, right? Because our p-value is not less than the alpha level. And what does that mean in terms of our water, probably very expensive water filtration system? No change. Womp womp. So our conclusion, right? Since you want to talk about all the things, incorporate the p-value, your alpha level, right? Really explain what's happened here. So since our one-sided p-value of 0.092413, right? Highlight that you know what it was, is not less than our assumed alpha level of 0.05. We do not have enough evidence to reject H naught. We do not have enough evidence to reject H naught. And then we have to answer the question. But at this point, you're tired and you always forget to do it. But it is important, especially if you're writing a report on your analyses. I'll paste this. Therefore, there is no evidence of so I'm hesitating because all I want from you is just take the question and reword it as an answer. That's all I'm expecting, right? Which would read, therefore, there's no evidence of a significant increase in the mean dissolved oxygen levels after the filtration system is installed. But you could also say, if you wanted to, right, there's no evidence of a change, right, after. But I'm just going to use the wording of the question just to match how I'm expecting you to do it, right? And then if you want to kind of put a little flair on it, you're allowed to, but I'm not expecting it to. Okay. And so there's no evidence of a significant increase in the mean dissolved oxygen level after the filtration system is installed. Can you imagine getting this report if you'd been the one to push for the filtration system? Major bummer. But it is what it is. Yeah. It does happen. I mean, it happens all the time. What's nice about being a statistician is it doesn't, you know, these are the numbers. There are consulting firms that do analyses. And so I used to work for a firm who did a lot of government contracts. So, but they even have their own I guess crew, but they farm it out a lot too. Yeah. Lots of stats being done everywhere. It's not so interesting if there's no difference, right, between the before and after. It would be more interesting if we did find that there is a difference, then we would probably follow it up with, okay, well, what was the difference, right? And that's where the confidence interval comes in. We're still gonna do it because, well, what was the difference, right? And so to determine the difference, we can build a confidence interval. Because we did not have enough evidence to reject H naught, I suspect that 0 will be inside my confidence interval, right? It will be one of those plausible differences from my confidence interval. Now, to match a one-sided test, right, we are going to build what confidence interval? So we said, okay, I've got, let's see, centered on 0 here. I forced my, my alpha to be 0.05, right? Putting all my eggs in one basket at 0.05. Okay. But my confidence interval has to be symmetric, which means that I also need to have 0.05 down here in order to match my conclusions. Okay. And so that means that I have 0.9 left in the middle, right? And so a 90% confidence interval should match my conclusion of a one-sided hypothesis test at an alpha of 0.05. Right? And so here I have 0.9. So the question might read something like this: construct a 90% confidence interval for the mean difference in dissolved oxygen levels. In dissolved oxygen levels. This mean difference here, this is mu diff, right? The mean of the differences. Whereas for two independent samples, then we were talking about the difference in the means. Yeah? So slight change of words that make a huge difference. But we want to make a 90% confidence interval, right? Then what do I need? I need to find, where's my pointer here? I need to find the T that makes this happen, right? And so here I get negative T star and T star. I've got the T dot inverse in Excel. And so we can say, okay, the T dot inverse, and I think it just wants the probability, let me see, and the degrees of freedom. Let me check. It'll prompt me, so I rely on that a lot. Equals T dot inverse. Oh, and I guess it does have the two-tailed, but I think the two-tail requires, it would be asking for the area in both the tails, and let's just do the T dot inverse. That probability is going to be the area to the left, right? So whether you use the negative T or the positive T, just pick whatever area you need. I'm going to use 0.05, remembering that I'm going to get a negative T, right? But that's okay. At 19 degrees of freedom again. Enter. Now let me just play around with this T dot inverse two tail, because I think that it would need 0.10 to match. Let me just check. It does. Oh, I wish I could remember how to show the formulas for both, but that's okay. I'll screenshot this though. Where this probability is the area to the left. So we do need to find our T star, but you can use Excel to do that. Oops. Crop. I'll just make a note here that this is T dot inverse dot two tail of 0.10 at 19 degrees of freedom. Whereas this matches this. Either way, this is for a 90% confidence interval. Okay. So our T star, this is a negative version of this, right? And it really doesn't matter. In fact, I think using the negative makes it a little bit cleaner because it turns your plus minus. Everyone wants to do the plus first, but that's the upper end, and then the minus. But if you have the negative one, right, then your plus turns into a minus, which makes it the lower, and the minus turns into a plus, which makes it the upper. But either way, doesn't matter. As long as you list your interval from smallest to largest, that's important. And so T star is going to be 1.729133. So our confidence interval, X bar diff plus minus T star. It's the only thing we really had to work for in this question. Square root of n diff S diff over the square root of n diff. And if you've calculated S diff over the square root of n diff, you can reference those cells, right? And building the confidence interval is pretty breezy. I had a mean of negative 0.4 plus minus 1.729133. I think I had 1.3 as my S diff. Let's see here. Yeah. Divided by the root of 20. A common mistake that I see is wanting to use the degrees of freedom instead of the n, right? And so, but that's my only kind of thing that tends to happen. Common mistakes. 1.3 divided by the root of 20 times 1.729133. I get negative 0.4 plus minus 0.5026396609. Negative 0.4 minus that, I get negative 0.9026396609 up to negative 0.4 plus that guy. Expecting a positive, right? Because I'm expecting 0 to be in my interval, which it is. 0.1026396609. Let's round this to 4 decimal places. 9026 up to 0.1026. Just because I lost interest after 4 decimal places. Right, if you're kind of looking here, well, 903 3 seems like kind of a stretch, but 9026, I wouldn't do any more rounding there, and so that's where I'm gonna end it. Right, that's kind of how I pick my decimal places. Once I lose interest, right? Once I stop rounding, essentially. Okay, so what's important is that this interval is for the mean difference, right? And so when we interpret it, our interpretation has to be in terms of the mean difference. So we use the same interpretation as always, right? We are 90% confident the interval from negative 0.9026 to 0.1026 captures the, and usually I throw in a true mean difference in dissolved oxygen level. That's really just to emphasize that it's for the population, right? Not just these 20 locations. We know everything there is to know about those 20 locations, right? We're trying to learn about the entire stream. So we're 90% confident that the interval from blah, blah, blah captures the true mean difference in dissolved oxygen levels. You can take it a step further and say, okay, well, if the mean difference is somewhere between negative 0.9026 and 0.1026, right? If we talk about before minus after, right? If before minus after, so this is extra, but we did before minus after. If it's equal to negative 0.9026, it means that the before was 0.9026 less than after, right? Or on the other side, you could say that the after is 0.9026 higher than before. Therefore, after is 0.9026 higher than before. Oops. And on the other end, if before minus after is 0.1026, then after is actually 0.1026 less than before. That's bad. Right?
Lower.
Higher, lower, yeah. Lower than before. Right. That is extra, but just to emphasize that we're talking about the average of the average difference, right? The mean difference. And so this means that if I'm 90% confident that the true difference or the true mean difference is somewhere between 0.9026 higher than before or 0.1026 lower than before, then 0 is a perfectly reasonable difference, right? And that's what leads us to say that there's no evidence of a difference, right? Not a significant difference. I'll say since a mean difference of 0 is in the interval, there is no evidence of a significant change. is in the interval. There is no evidence of a significant change. Change because it's a confidence interval, which you can only use to do a two-sided test. And I feel like I have a lot more to say, but the end of this new material. We still have next week, but you did it. Now you get to go back and have an overview. If you have any questions, let me know. Otherwise, enjoy your weekend and good luck on your midterm.